Linear algebra part 5. In this part, or in this section, or chapter if you will, we're going to address the system of linear equations and how to resolve them using matrices. At first, what is a system of linear equations? It is a system or a collection of two or more linear equations involving the same set of variables. As an example, 2x plus y equal 5, x minus 3y equal minus 4, and the number of equations should be equal to the number of variables for the system to be resolvable, for us to be able to solve the system. So let's say you have n variables and m equations, okay? So at least the number of variables should be equal, okay, to the number of equations or less than, so that we can solve the system. Okay, it has the form of a times x equal b. B is actually the solution vector, okay, which is a column solution vector. It has a format of a column. X is the set of variables, so you have x1, x2, x3, xn. It would be also a column vector starting from x1, x2 all the way to all the number of variables. And a being, the different values, arguments multiplied by the different variables from the first line all the way to the last line, the last equation, okay? So A11 is element in this matrix at the first row, first column, first row, second column, first row, third column, etc. Then second row, first column, okay. You start noticing the pattern. So A is mn coefficient matrix having m lines and n columns. X is the column vector of variables, okay, containing x1, x2 all the way to xn, and B is the column vector of constant, which are the solution part, like the result part of the equations. So in this case, it would be 5 minus 4, a column vector containing 5 and minus 4 respectively. So to represent this system of equations here, A is equal to A11, A12, A13. So the arguments multiplying the different variables in the first equation, you set them in the first line, then those multiplying the arguments in the second equation, you place them in the second row respectively, A21, A22, all the way to the last argument, okay? Finally, you have also x, which is the vector of the different variables or unknowns containing x1, x2, all the way to xn, okay, in a column setting. Then B, it has the solution part, not the solution, meaning like the result of this equation, okay? The latter part, or like the second side of the different equations. So it is a column vector containing B1, B2, all the way to Bn, okay? The last value. Okay. So a system of linear equations consists of multiple equations involving the same set of variables. For example, you have 2x plus y minus z equal 8, minus 3x minus y plus 2z equal minus 11, minus 2x plus y plus 2z equal minus 3. Three equations having each three unknowns or three variables. So we can write this system in matrix form, which is A times x equal b, A being the coefficient matrix, holding 2 minus 3 minus 2, 1 minus 1, 1, minus 1, 2, 2. X is the column vector of variables containing x, y, and z. And B is the constant vector, which is the vector containing respectively 8, minus 11, minus 3. You have elementary row operations, one of the method, which is to solve the systems, we often transform the augmented matrix AB, okay, using elementary. Like this was the same method by which we've discovered, or like we've gotten the inverse matrix, okay, not too long ago. like a few slides back. So what are the different row operations? The ones that we've seen already, like row swapping. It is more than that. You can swap or interchange two rows, swap them together. Row scaling, you multiply a row by a non-zero scalar. Row replacement, like R1, for example, equal R1 plus 2R3. You see, this is row replacement. We've seen it already. Like Ri would be exchanged by Ri plus KRJ. Okay, so it is the original line added to a scalar number multiplying another line, another row. By line, I often mean row. Okay, and the result is replacing Ri, the original row. So we add a multiple of one row to another row. REF, or row echelon form. A matrix is in row echelon form if all non-zero rows are above any rows of all zeros. Okay, that's first. Then the leading entry or pivot of each non-zero row is to the right of the leading entry in the row above it. All entries below a pivot are zero. As an example, okay, so all non-zero rows are above any rows of all zeros. We don't have a row of all zeros here, okay, but you notice something, so that 1, 2, minus 1, 3, you have here 0 to the left, then it keeps shifting, okay, to the right, like as you go down with the rows, as we mentioned here, the leading entry pivot. Okay, what is a pivot at first? So 1 is a pivot. Why? Because all the values underneath it are 0. All entries below a pivot are 0. Okay, so 1 here is a pivot. Also 1 over here is a pivot. 4 is a pivot because all the values underneath it are 0. Okay, now more than that, the leading entry of each non-zero is to the right of the leading entry in the row above it. Okay, so this is the leading entry of this row, correct, of the first row. Now the row below it, okay, its leading entry which is the first value that is different than 0, okay, is to the right, correct, is to the right side of the leading entry in the row above it. Okay, so here, like the third row also, the leading entry, which is 5, is to the right side, okay, right to the leading entry of the row above it, which is 1. Okay, so as you go downstairs, each row will have a leading entry which is to the right of the leading entry of the row above it. Okay, so you keep shifting to the right as you go downstairs. This is what will make up or form or create what is called a row echelon form. In other words, it's like more likely or more likened to a triangular matrix, although it's not perfectly triangular, okay, but it is so close to that. So as we mentioned, all non-zero rows are above any rows of all zeros. Then you have the leading entry. Okay, we don't have any all zero row here, but the leading entry of each row is to the right of the leading entry of the row above it, which is 5 in comparison to 1, then 1 in row 2 in comparison to 1 in first row. Each one is to the right of the entry above it, to the right of the entry above it. Then all entries below a pivot are 0. Okay, so below this pivot, all the entries are 0. This pivot here, which is 1, the entry below it is 0. And also for 5, actually 5, there's nothing below it. Okay, so you have, this is also a pivot, which is, third row, fourth column. Okay, this is not a pivot because it's not part of the leading entry, so to speak. Another important concept is the REF, which is the reduced row echelon form. Okay, what is a reduced row echelon form? It is an REF which has each pivot within the matrix being 1. Okay, so it is an REF except each pivot or each leading entry within each row, okay, that is different than 0 and below which all the other values within the column are 0. So each pivot is 1, not anything else. And each pivot is the only non-zero entry in its column. So each pivot is the only non-zero entry in its column. As an example, let's see if this complies with the RREF, reduced row echelon form criteria. So each leading entry should be 1 in each row, correct? So let's check it out. This is the first entry, 1, 1 in the second row, and 1 in the third row. And these entries are pivot. Why? Because under each of these entries, you have all the other values are 0. Okay? It is the only non-zero entry in its column, which is correct. Okay? This is the only entry that is non-zero within its column. Not only that, all the values below this one are 0, but also the above. So it is the only value within the column that is different than 0. Okay? So you have, for this to be an RREF, okay, reduced row echelon form, to break it in a more simple way, you need for each leading entry, for each row, to be 1, but more than that, all the other values, not only underneath that leading entry, but even above it within the same column, all the other values should be 0. So you have 1, 0, 0, 0. 1, 0, and 0. 0, 0, 1. Which makes it RREF. Okay, example, solve a system using row operations like the system below, formed of 3 linear equations, x plus y plus z equals 6, 2y plus 5z equal minus 4, 2x plus 5y minus z equal 27. You can pause the video and try to solve it first before we get into the solution. Alright. At first, we need to write the augmented matrix. So we place all the values of A, which is 1, 1, 1, 0, 2, 5, okay, because x here is multiplied by 0. That's why we don't have x to begin with. So 0, 2, 5, and the third row, 2, 5, minus 1, okay? And you place on the other side 6 minus 4, 27, okay? And we need to make it a triangular, like triangular format, triangular matrix, okay? We will check how to evaluate that, how to get there. Okay, so you have 6 minus 4, 27. Okay, now, first operation, let's apply, we need to get rid of this 2 here. So R3, okay, is equal to R3 minus 2 R1. R3 minus 2 R1. Let us check it out. Okay, so R3, 2, 5. Sorry, let me try to write it in a more neat way. Okay, so R3 is R3 minus 2 R1, which is, okay, this is R3, 2, 5 minus 1, 27, minus 2 times R1, okay, minus 2, minus 2, minus 2, minus 12. Let us add them together and we place it back into the first, I'm sorry, we place this line back in the third row, R3, okay, so you have 0, 3, minus 3, and 15, and you get this. 0, 3, minus 3, 15, so far, okay? Very good. Now we need to get rid of this value here to make it 0. So let me check it out and let us clean the slate. Okay. Now, to get rid of this value, we've done R3 is equal to R3 minus 3 divided by 2 R2. Okay? So R3, yeah, we multiply R2 by minus 3 divided by 2 to get rid of the 2, and we get minus 3 here. Okay, so when we add them, we get 0 on the third row. Get it? Okay, so let me rewrite it. So you have R3 is equal to R3, which is 0, 3 minus 3, 15, minus 3 divided by 2 R2, which is, okay, 3 divided by 2 times 0 doesn't matter, minus 3 divided by 2 times 2, which is minus 3, 2 cancels out, then minus 3 divided by 2 times 5, which is minus 15 divided by 2, and then minus 3 divided by 2 times minus 4, minus cancels out, 4 divided by 2, 2, so it is 6, okay? Then, okay, so it gives us, yeah, actually we resolved it. Okay, so yeah, we need to add them together and place them in R3, so you get 0, 0, then minus 15 divided by 2 minus 3, okay, we've gotten minus 10.5, then 6 plus 15, 21, okay, and you see, now all that remains is this value to be removed. Okay, so we complete using the same concept. Okay, now from the last row, okay, yeah, you don't need to do any changes, any other changes. Now we can immediately find the values for z, y, and x. Okay, so you have minus 10.5, which is on the z column. So minus 10.5, z is equal to 21. So z is equal to minus 2. Okay, we found z. Now z, we can replace it in the second equation here. So what is the second equation? It is 2y plus 5z is equal to minus 4. Okay, so 2y plus 5z is equal to minus 4. What is z? Z is equal to minus 2. So 2y plus 5 times minus 2 is equal to minus 4. So 2y minus 10 is equal to minus 4. It becomes plus 10 minus 4, which is 6. Then y equal 3. Finally, we end up with the last one, which is x plus y plus z is equal to 6. You already have y, which is 3, and z, which is minus 2. So x plus 3 minus 2 is equal to 6. 3 minus 2, 1. You move it to the right, becomes minus 1. So x is equal to 6 minus 1, which is 5. Like Gauss pivoting. Now, when a system of linear equations has infinitely many solutions, so it's called a dependent system, we can express the solution set using 3 parameters. So we need to parameterize some of the unknowns. A parameter is a variable we choose freely, and the other variables are written in terms of this parameter. So other variables would be subject of that parameter. So we consider it, or we treat it as if it was a constant. During Gaussian elimination or Gauss-Jordan that we've seen moments ago in the previous slide, we sometimes end up with fewer pivot columns than variables. The non-pivot variables become free variables. These are assigned parameters like t and s. This is the case where you have the number of equations is less than the number of variables. For instance, if we go back to the former example, okay, let me go back. So let's say we cannot solve z. Why? Because, yeah, consider we had only 2 equations. Like, for instance, x plus y plus z is equal to 6, and 2x plus 5y minus z is equal to 27. How would you resolve that equation? Which is, again, x plus y. How to resolve that system? X plus y plus z is equal to 6. And 2x plus 5y minus z is equal to 27. Pretend that we didn't have 3 equations. So the number of parameters, or the number of unknowns or variables, which is 3, is greater than the number of equations, which is 2. In such case, you need to parameterize one of the variables. Z in such case. Consider Z as being a constant. You take it as t, as if it was a constant here. So you get x plus y plus t is equal to 6, and 2x plus 5y minus t is equal to 27. Therefore, what you get, a new shape of the system, x plus y equals 6 minus t, as if 6 minus t is a constant altogether, and 2x plus 5y is equal to 27 plus t. In such case, you resolve the system as if t is a constant. This is how you move on when you have the number of equations is less than the number of variables. Example, and let us assume that we cannot resolve this equation, but the fact is, this system rather, the fact is it is resolvable without the usage of parameters. Why? Because the number of variables is equal to the number of equations. But let us suggest that we need to use or parameterize one of the variables. So we have x plus 2y is equal to 5, 2x plus 4y is equal to 10. Let's at first start with attempting to row reduce. Okay, you have 1, 2, 5, 0, 0, 0. Okay, yeah, you can resolve it using that method. Okay, so the equation x plus 2y is equal to 5. Let y be equal t as a free parameter. So x is equal to 5 minus 2t. Parametric form, x equal 5 minus 2t, y equal t. Okay? So the equation become, or as a vector, you can put it this way. So x is equal to, you have 5 minus 2t, okay, which is, we replaced y by t, and x became 5 minus 2t, okay? So 5 plus t times minus 2, okay? And you have 2x plus 4t equal 10, so 2x equal 10 minus 40. X is equal 10 divided by 2 minus 40 divided by 2, or 5 minus minus t, okay? 5 minus t, something like that, yeah. So it becomes, okay, 0 plus t. Yeah, this is the other equation. Okay, regardless. So you have on the second row, since we've parameterized, okay, so the first argument is for the one belonging to x, the second belonging to y. This should not be x in such case. This should be capital X, referring to the entire equation. So x is equal, or big X is equal to 5 minus 2t. So this is the x argument, 5 plus t times minus 2, and y equal t. So yeah, let us rewrite it so that it can become clear. So xy is equal to, respectively, okay, x is 5 plus minus 2t, okay, and y in the second row is equal to 0 plus t, okay, because it's not multiplied, and you don't have any other like free value. You only have, so this is 0, you only have t multiplied by 1, okay? Another way to rewrite it. Another method to resolve the system of equations is to use the inverse matrix method, which implies that you have the original form is ax is equal to b, with a is all the arguments multiplying the parameters, correct? The different variables. You extract them, like you simply write it by ignoring the x, y, and z as a matrix, okay? Then multiplied by x, which is the set of variables which are respectively x, y, z, is equal to b, or the constant part of the equation, okay? B is the vertical or column vector formed of 4, 2, 10, respectively. So ax equal b. How to get x, which is the different values, like the values of the different variables? X is equal to simply a minus 1 times b. with A minus 1 being the inverse matrix, multiplied by B. This is how you get X, or big X, capital X, which is actually the set of these different variables, X, Y, and Z, okay? The column vector containing the three variables, in this case, for that system of equations, respectively X, Y, and Z. Now, I have deliberately hidden the solution so that you can take a stab at it. If you want to try to resolve it yourself, you can pause the video and try to solve it using this method, which is X. X, again, is actually the vector, the column vector X, Y, Z, equal to A minus 1 being the inverse matrix, multiplied by B, which is the column vector formed of the constants, which are the right side of the three equations, formed by 4 to 10 respectively. Let's check the solution. So what is A minus 1? Mind you that A minus 1, the inverse matrix, is equal to 1 divided by that of A, determinant of A, multiplied by the transpose of the cofac of A. First of all, that of A is equal to 2 multiplied by minus 1 times 1, minus 2 times 2. Let us get the pen again. So it's 2 multiplied by minus 1 minus 4, basically. Then minus 1, so you have plus, minus, plus. Then minus 1 multiplied by 1, minus 3 times 2, so 1 minus 6. Then minus on the outside, minus 1 times 1 minus 6. Then finally, here you have minus 1, but the sign from the outside is plus. Okay, so minus 1 multiplied by 2 minus 3 times minus 1 plus 3. So minus 1 times 2 plus 3 is equal to 10 minus plus 5 minus 5 equal to minus 10. The cofac of A. How to get that? Again, as a reminder, so the first value here, you need to cross both the line or the row and the column intersecting at this point, and we need to only keep the sign for this element, which is plus, without the element itself, and you find the determinant of this matrix over here, which is minus 1 minus 4, which is minus 5 times plus 1 times a plus, so it stays minus 5. This is the first value. This value here, for example, you have plus, minus, plus, minus. This one is minus, okay? The sign for this one is minus. What is the value for that? You cross, or you like bar down both the intersecting column and line. We are left with this matrix here, which is determinant for this small matrix is 1 minus 2 times minus 1, which is plus 2. 1 plus 2, 3, and you have minus on the outside is minus 3. This here, okay? And the position for the result would be first column, second row, where these two lines have intersected. Remember, you start from left to right, plus, minus, plus, minus, plus, minus. The sign for this element here is minus. What would be its value? And it would be located, the result is located at the third column, second row. So let us evaluate that. 4, 2 times 2, 4, minus 3 times 1, so 4 minus 3 is 1, and you have minus on the outside, it would be minus 1, and this is the value, minus 1, etc. You do it for all the other elements. Now, after that, we need to evaluate or like get the transpose of cofac A. How we get the transpose? You simply flip the columns into rows, or vice versa. Okay, so this row, this column becomes row, or the row becomes a column. Okay, so in other words, this row becomes a column, means minus 5, 5, 5, but in column 4. Okay, you rotated 90 degrees. Then minus 3, 5, minus 1 becomes minus 3, 5, minus 1 in column format. Then 1 minus 5 minus 3, 1 minus 5 minus 3. So this you multiply by 1 over minus 10, and you get the following. So this is A minus 1. we still need to multiply it by b, which is 4 to 10 to get x, y, and z. So x is equal to the inverse of matrix A, or A minus 1, multiplied by b, which is this constant vector. Okay, so x is equal to 1 divided by 2, 3, 10, minus 1, 10. This is A minus 1, basically. Okay, minus 1 half, minus 1 half, 1 half, etc. Multiplied by 4 to 10. Okay, so let's multiply them. We multiply the row by the column, as we've seen earlier in any matrix multiplication. And we can multiply them. Why? Because the number of columns here is equal to the number of rows here. So the number of columns in the first matrix is equal to the number of rows in the second matrix. In other words, J is equal to I. Okay? J, the number of columns in the first matrix, is equal to that of the rows in the second matrix. Okay, so 1 half multiplied by 4, which is 2, plus 3 divided by 10 multiplied by 2. Okay, so 3 divided by 5. Then minus 1, 10 times minus 1 divided by 10 multiplied by 10, which gives us minus 1. That would be the value of the first row, okay, which is 8 by 5. And remember, the resulting matrix would be equal to the number, like its size would be equal to the number of columns. Okay, its rows, it would have its number of rows would be equal to the number of rows, so to speak, of the first matrix. Number of columns would be equal to the number of columns of the second matrix. So 3 rows, 1 columns. Okay, 3 rows, first row, second row, third row, and 1 column. This is the resulting matrix. Okay, so 2 plus 3 divided by 5 minus 1 is 8 divided by 5. Then you have, okay, let's multiply the second row with this column. Okay, so 4 times minus 1 divided by 2, which is minus 2. Then 2 multiplied by minus 1 half, which is minus 1. Then 10 multiplied by 1 half, which is 5. Okay, equal to 5 minus 3 equal to, which is what? This is y. Okay, this is the y value. Finally, you have third row multiplied by the column. Okay, so we have minus 1 half times 4, which is minus 2. Then 1 tenth multiplied by 2, which is 1 divided by 5. Okay, we add it up. Then 3 divided by 10 multiplied by 10, which is 3. Okay, and this is the final answer. You have x is equal to 8 divided by 5, y equal 2, and z equal 6 divided by 5. Now let us resolve the same system using Gaussian elimination, okay, method. Now, how to go about it? Okay, as a reminder, you place the A matrix, and here's how we break it down. So you have x, y, z, the system of variables. We already know that. You extract them, or you extract the values multiplied by them, and you place them in A matrix, which is formed by respectively 2, 1, minus 1, the first row, 1, minus 1, 2, second row, and 3, 2, 1, the third row. This is the A matrix. As for B, which is the constant part made of a column vector, okay, and the following elements, 4, 2, 10, that would be, you know, the constant vector. Okay, so we place A on the left or to the left and B to the right, and we try to minimize, like through row or Gaussian elimination, to triangularize, to make this matrix to the left a triangle format. Okay, but you cannot do it to A alone. Okay, it needs, like, you need to have the entire system of the equation. So you need A from the left, on the left, and B to the right. Okay, separated by this separation line. And you triangularize A and B next to it in a way to make it more simple to be resolved. Okay, so you can think about it right now. You can pause the video, try to resolve it yourself. After that, we will solve it together. All right, now, so A next to B, or B to the right side of A, is done this way. Okay, so we place A, which is 2, 1 minus 1, 1 minus 1, 2, 3 to 1 to the left. Then you have a vertical bar separating it from the right side equation, which is the solution set, not the solution, I'm sorry, the constant part of the equation, made of 4 to 10. Okay, now we need to start eliminating these lower values, the values that are, below the diagonal. We need to make them 0. This is the diagonal, 2 minus 1, 1. Let's start. You always start with the leftmost value, the lowest leftmost, which is 3. How to get rid of 3? Like, we can create the combination R3 is equal to R3 minus 3 R2. R3, which is 3, 2, 1, 10, minus 3 multiplied by R2. We combine them together and we place the result in row 3. Let us check it out. R3 is equal to R3 minus 3 R2. What is R3? It is 3, 2, 1, 10. 1 and 10. Minus 3 R2. Minus 3 times R2, which is minus 3, the second row. Minus 3 times minus 1 is plus 3. Then minus 3 times 2, which is minus 6. And minus 3 times 2, minus 6. Okay? You add them together, you get 0, 5, minus 6 plus 1, minus 5, and minus 6 plus 10, which is 4. This is row 3. 0, 5, minus 5, and 4. Now, the second combination is we need to get rid of this value here, the 1, in the second row. Or we continue with the third row. Let me check. Yeah, this one in the second row, we need to get rid of it. The combination we need is R2 is equal to R2. So we multiply by 2 and we subtract the first row. This is how we do it. So R2 is equal to R2 minus R1. Let us check what is 2R2 minus R1. This is row 2. 2 times R2 is 2 minus 2. We are multiplying this row by 2. 4 and 4. So this is 2R2 minus R1. What is R1? Minus 2 minus 1 plus 1 and minus 4. We add them up and we place them in R2. Let's add them up. You have minus 2 plus 2, 0. Minus 3, 5. And finally 0. You replace R2 with them. Okay, so you replace them by R2, or you replace R2 with this result, which is 0 minus 3, 5, 0. Now, what do we have? After that, I need to clear this value, this 5 over here. So how to do that? You can evaluate R3 is equal to R3 minus, we can do it using the second row. So you multiply this row with 3 and the one above it with 5. So you get 15 and minus 15. Yeah, R3 is equal 3R3, so that we get 15 here, plus 5R2, because 5 times minus 3 is minus 15. 15 minus 15 is 0, so this is annihilated, which is the point. Let us check it out. 3R3 is 0, 15 minus 15, and 3 times 4, 12. 5R2 is 0, minus 15, 25, and 0. You add them up, so 0, 0, 25 minus 15 is 10, and 12. You finally place them in the last row, which is 3, and you get this final matrix. Great. Now, if you notice something, this has become much easier to deal with. So you have 10z is equal to 12. You can immediately get the value of z, then you place it in the equation above, which is minus 3y plus 5z is equal to 0. So y is equal to 5 divided by 3z, and you've already solved the equation. Okay, but let us see So then z is equal to 12. So z is equal to 6 divided by 5, which is 12 divided by 10, okay, with a reduction or like a factorization rather. Then minus 3y plus 5z is equal to 0. So minus 3y plus 5 multiplied by 6 divided by 5, which is 6, is equal to 0. So y is equal to, then for x, you have 2x plus y minus z is equal to 4. You replace y and z, y by 2 and z by 6 divided by 5, and you have 4. So you get x is equal to 8 divided by 5. And that is the solution using the Gauss pivot method. Now let's use Kramer's rule to get the same result. Okay, so you can pause the video, try to resolve it on your own. As a reminder, Kramer's rule depends on evaluating at first the determinant, delta, for A. Then you have x is equal to delta x over delta y equal delta y over delta. What would be delta x? Simply to get delta x, you replace the first column by the constant vector. Okay, that would be delta x. You get the determinant for that, and you divide it by delta to get x, to get the value of x. For y, y is equal delta y divided by delta. You simply replace, or you replace the second column by the constant vector. So instead of 1 minus 1, 2 in the middle, you replace it by 4, 2, 10. You resolve delta y and you divide it by delta, which is the determinant, etc. Okay, so try to resolve it yourself and we will get back to the solution. First of all, determinant of A, that of A, or delta, which is equal to 2 multiplied by minus 1 minus 4. Okay, 2 multiplied by minus 1 minus 2 times 2, which is minus 4. Then you have minus 1 multiplied by 1 minus 6, correct? Finally, you have minus 1 multiplied by 2 plus 3. So minus 1 multiplied by 2 plus 3 equal to minus 10 plus 5 minus 5 equal minus 10. To find delta x, we replace the first column of A with column matrix B. Okay, so this is delta x. How do we actually do that? So you completely remove the first column within the A matrix and you replace it by 4, 2, 10, which is the solution, not the solution, I'm sorry, the constant vector. Okay, 4, 2, 10. So delta x is equal to 4 to 10 instead of 2, 1, 3. Then whatever remains, you leave it as is. So which is 1 minus 1, 2, the second column, and minus 1, 2, 1, the third column. Now, we need to evaluate the determinant delta x, okay, which is equal to 4 multiplied by minus 1 times 1 minus 4, so 4 times minus 1 minus 4. Then minus 1 multiplied by 2 minus 20, correct? Finally, minus 1 here and the sign would be plus. Okay. Multiplied by 4 minus 10 times minus 1, which is 10. So 4 plus 10 multiplied by minus 1 equal minus 20 plus 18 minus 14 equal minus 16. Okay. Same thing for delta y. We replace, in such case, the middle column with column matrix B. So the middle column, which is 1 minus 1, 2, is replaced or should be replaced by 4, 2, 10. And you evaluate delta y. So you get 2 multiplied by 2 minus 20. Then minus 4 multiplied by 1 minus 6. Then minus 1, which is, it remains minus 1 multiplied by 10 minus 3 by 2, so 10 minus 6, equal minus 20. This is delta y. Then, to find delta z, we replace the last column in A by column matrix B. So the last column, which is minus 1 to 1, should be replaced by 4 to 10. Okay, so delta z, let's evaluate it, is equal to 2 multiplied by minus 10 minus 4, correct? Then minus 1 multiplied by 10 minus 6, then plus 4 multiplied by 2 minus 3 minus 1, which is plus 3, equal minus 28 minus 4 plus 20 equal minus 12. So delta x is equal to minus 10, delta y minus 20, delta z minus 12, and delta, we know that it is minus 10, the first value that we've got. So x is equal to delta x divided by delta, or minus 16 divided by minus 10, equal 8 divided by 5. The same value we've gotten using the Gaussian elimination method in the previous example. Okay, in the previous execution, it's still the same exercise, the same system of equations. Okay, now y is equal to delta y divided by delta is equal to minus 20 divided by minus 10, which is equal to also same value we've gotten before. Then finally z is equal to delta z divided by delta, which is minus 12 divided by minus 10, or 6 divided by 5. Now let's talk about vector spaces. Okay, so vector spaces and subspaces, definition of a vector space. A vector space or linear space over a field F is a set V equipped with two operations. You have vector addition plus, okay, V cross V gives us V, takes two vector U and V within V space and produces another vector. Okay, so if U belongs, or like it is existing in V and lowercase v exists in V, hence U plus V exists in uppercase V. Okay, V being the domain here, the set. Okay, so if U and V exist in capital V, which is the set here, not the vector, then their sum, which is U plus V, also exists in V. Okay, so U and V produce another vector also existing within the same set. Scalar multiplication, so F times V, which is the field F here, multiplied by V, gives us V, the set. So take a scalar A within F and a vector V within the set V, and we can produce A multiplied by V will still exist. It will form a new vector still existing within the same set. Okay, these operations must be satisfied, or must satisfy the 8 following axioms, so that it would be, the system would be a vector space, so that we would be talking about a vector space. Axioms of a vector space. Okay, for all U, V, W being three vectors that exist in a set V, and all scalars A and B existing in a field F. A field is the field, belonging or covering the set V. Okay, so we have the following characteristics. At first, you have a closure under addition, which means U plus V also exists in V, set V. Commutativity of addition, which means U plus V is also equal to V plus U. So if you flip the order, it doesn't matter. Associativity of addition, in other words, U plus V together added to W. So if you add U plus V at first and the result you added to W, it's equal to U plus V added to W. It is equal to U plus V plus W. Additive identity. So there exists a vector 0 within V such that U plus 0 is equal to U additive inverse for every U within V. There exists minus U also belonging to the same set, which is V, such that U plus minus U is equal to 0. Okay, so these are different conditions that must be satisfied for us to have a vector space, in case you're still wondering. 6, closure under scalar multiplication, which means A times V, A being the scalar, the part, or which is a part of the field F, and V vector belonging to set V. So A times V should exist within V, the set. Then distributivity of scalar over vector addition. So A times U plus V should be equal to A times U plus A times V. 8, distributivity of scalar addition. So A plus V plus B times V should be equal to AV plus BV. Then associativity of scalar multiplication. So ABV is equal to AB times V. Okay, the same thing. A and B being the scalars and V the vector. Multiplicative identity. So 1V equal V, where 1 is the multiplicative identity in F. Okay, it is the identity where when you multiply it by V, V remains V. Okay, it gives you back V without any alteration. Examples of vector spaces. So R to the power of n with usual addition and scalar multiplication over F equal R. The set of all polynomials Pn of degree less than or equal to n over F equal R or C. Set of all continuous functions CAB over R. Okay, so you have R to the power of n with usual addition and scalar multiplication over F, with F is equal to R. So when you raise the power of R, you're still within the same, you're still a vector space. Or the set of all polynomials Pn of degree less than or equal to n over F equal R or C. Set of all continuous functions C between A and B over R, where A and B, both of them exist within R, okay, belong to R. Subspaces, a subspace W of a vector space V over the same field F is a subset of V that is itself a vector space under the same operations as V, okay, but it is a subset. Okay, subspace test, a non-empty subset W is included within set V. It is a subspace if and only if, first of all, 0 vector belongs to W, so 0 exists in W. It should be closed under addition if U and V are within W, so then U plus V also should exist in W, and closed under scalar multiplication. So if U exists in W and A exists in the field F, then AU should exist in W, okay, because W is a subset of V, so it applies, like it is ruled by the same laws, by the same premises, except, what's happening in W, okay, it applies to W first and foremost, okay, not only in V, but it should also apply to W. If these hold, all other vector space axioms are automatically satisfied because they come from V. So if these conditions hold, then all other vector space axioms are automatically satisfied since W belongs to V, since W is included as a subset inside of V. As an example, 1, 0 subspace, so let's say W is equal to 0, 0, 0. Trivial subspace contains only the 0 vector, okay? This is an example. A subspace within V, okay? Definitely 0, 0, 0 belongs as a subspace in V. Now, the whole space, so W is equal to R3, this is the entire space of real numbers. This is what we mean here, okay? Trivially, a subspace a plane through the origin. So let's say you have a plane crossing the origin. So W is equal to x, y, z within R3, plus 3 dimensions. So x plus y plus z is equal to 0. Why? Because it's crossing the origin. Closed under addition and scalar multiplication contains the 0 vector. Okay? It contains the 0 vector. A line through the origin. So let's say W is equal to t, 1, 2, 3. These are the parameters of this line. Okay? Parametric equation, so to speak. And t should be within R. Vector spaces. A vector space or linear space is a set V together with two operations. You have vector addition, u plus v is within v for all u and v are within v. You might notice that this is a kind of a repetition, but it's kind of important so that we can re-emphasize some notions that we've seen before. So vector addition is still under the same set, still belongs to the same set when u and v belong to v, which is also the set V. Scalar multiplication, so C times V, C being a constant here, belongs to V for all scalar C that belong to F, the field which is a part of V, and V belongs to V. Now, it must satisfy 8 axioms as we've mentioned before: commutativity, associativity, identity, inverses, distributive laws, etc. Examples: Rn, where n tuples are tuples of real numbers, the set of polynomials of degree less than or equal to n, and the set of all m times n matrices. Subspaces: a subspace W of a vector space V is a subset of V that is itself a vector space, but it is a part of a bigger vector space which is V. Okay? And it's controlled or governed by the same operations. So again, the conditions for a subspace W, we've seen it already. There might be a repetition here. So conditions for a subspace W to be existing is that 0 should be a 0 vector contained within W or existing in W. If U and V belong or exist in W, then U plus V also exists in W subspace. If V exists in W and C exists in R, then C times V exists in W. Okay, C being the scalar existing in, among the real numbers. So C times V still exists as a vector, okay, belonging within W, within the subspace. Okay, and since it belongs or it exists in W, then definitely it exists in V, which is the larger vector space, of which the subspace is only a part of it. As an example or examples, like the x-axis in R2 is a subspace. The set of all solutions to a homogeneous system, Ax is equal to 0, is a subspace within the larger space. Span. What is the span of a set of vectors, which are v1, v2, etc., all the way to vk? The span is the set of all linear combinations of these vectors. So span of v1, v2, all the way to vk is equal to c1, v1 plus c2, v2 plus c3, v3 all the way to ck, vk, with c is being a number, okay, belonging or existing in R within the real numbers space. Geometrically, the span is the space generated by those vectors. Example in R3. Okay. Span of one non-zero vector is equal to line passing through the origin, as an example. Span of two linearly independent vectors is equal to a plane going through the origin, and span of three linearly independent vectors equal all of R3, the entire thing. Basis. A basis of a vector space V is a set of vectors that is linearly independent and spanning V. Okay? They are spanning V. This means that every vector in V can be uniquely written as a linear combination of basis vectors. Example, standard basis for R2, okay, which is two-dimensional here, is 1, 0, 0, 1. Two uniquely written, two unique vectors, okay? Now, standard basis for R3 is 1, 0, 0, 0, 1, 0, and 0, 0, 1, from which you can make up whatever vector you want, okay, as you add them together, okay? So first vector plus second vector, you get 1, 0, 1. First plus second, 1, 1, 0, second plus third, 0, 1, 1, etc. Okay? Dimension. The dimension of a vector space V is the number of vectors in any basis of V. Okay, this is the dimension. So, dimension of the solution space of a homogeneous system is equal to number of free variables. Let's say, okay, if the dimension of W is equal to K, then any basis of W has exactly K vectors. And we're going to see examples afterward to break it down to make it more simple. As a summary, the span describes the set generated by vectors. The basis is the minimal set of independent generators from which you can combine and you can get whatever set of vectors that you want. And the dimension is the number of basis vectors or the size of the space. Linear independence, a set of vectors v1, v2 all the way to vk in a vector space V is said to be linearly independent if the only solution to c1 v1 plus c2 v2 plus ck vk equals 0 is the trivial solution c1 equals c2 equals ck equal 0. This means none of the vectors can be expressed as a linear combination of the others, okay? Examples 1, 0 and 0, 1. They are completely independent. This is called linear independence. And this is R2, meaning you have the dimension of 2 or 2 elements only, okay? For R3, 3 elements, 1, 2, 3, 0, 1, 4, 0, 0, 0. Now, this one, okay, is it dependent or not? This one is not dependent. Why? Because of the 0 vector. You can like combine 2 together to form another. You have one that is dependent on another, like 1, 2, 3 plus 0, 0, 0. You get from it 1, 2, 3. Not a unique vector, but the same vector. That's why it's not independent. Linear dependence. A set of vectors v1, v2, vk is linearly dependent, which is the set is linearly dependent, if there exist scalars, not all 0, such that c1 v1 plus c2 v2 plus c3 v3 all the way to ck vk is equal to 0. This means at least one vector can be written as a linear combination of the others. Examples. Okay, let's consider 1, 2, and 2, 4 in R2, okay? Now, this set is dependent. Why? Because the second vector 2, 4 can be written as 2 multiplied by the first vector, okay? So 2, 4 is equal to 2 multiplied by 1, 2, which means that it can be, obtained through a linear combination of 1, 2 multiplied by 2, hence it is dependent. Another example, in R3 you have 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 1 is dependent, given that the fourth vector is a sum of the first 3. So 1, 0, 0 plus 0, 1, 0 plus 0, 0, 1 gives us 1, 1, 1. So the fourth one is a combination, a vector sum of the first 3 vectors. Quick tests, 0 vector test. If the set contains the 0 vector, it is automatically dependent. More vectors than dimension. So if you have more vectors than dimension, like here, instead of having 3 vectors only, you have 4. So any set of more than n vectors is dependent, correct? And matrix method, put the vectors as column in a matrix. If the matrix has full column rank, the vectors are independent if they have full column rank. So again, if we have a 0 vector, it means that the set is dependent. If you have a larger number of vectors than the dimension, so here the dimension is 3, we should have only 3 vectors, okay? So automatically, if you have 4 vectors and the 1, 1, 1 being the fourth, then the set is dependent, okay? These are automatic tests, but the inverse is not always correct, meaning that it doesn't mean that if you only have 2 vectors, it means that the set is independent. Why? Because here in the first example, we've noticed that 2, 4 is a combination of linear combination of the first vector multiplied by 2. So it's not always the case. Row space, the row space of a matrix A is the subspace of Rn spanned by the rows of A. Okay. So it is the subspace of Rn spanned by the rows of A. If A is an m by n matrix, then each row is a vector in Rn. Okay? So row A is equal to span rows of A, different rows of A. The dimension of the row space is called the row rank. The row space doesn't change under elementary row operations. So row reduced echelon form RREF gives a convenient basis for the row space. Column space. The column space of A is the subspace of Rm spanned by the columns of A. So the columns are the constituents of the span within column A. Okay, so the column space is exactly the set of all possible outputs of the linear transformation x to ax. The dimension of the column space is called the column rank. Fundamental theorem of linear algebra, row rank A is equal to column rank of A. This common number is just called the rank of A, okay? So dimension is the number of rows within each of the columns. Null space kernel. The null space or kernel of A is the set of all solutions to the homogeneous equation. Okay, this is the null space or kernel of A. So given NA is equal to X existing in Rn with AX equals 0, the null space is always a subspace of Rn, of course. The dimension of the null space is called the nullity. The rank nullity theorem for an Mn matrix A, rank of A plus nullity of A is equal to n. Rank is equal to dimension of column space. Nullity is equal to dimension of null space. Okay? So the rank is equal to the dimension of column space. The nullity is equal to the dimension of the null space. Example. Let's take this 3 by 3 matrix of 3 rows and 3 columns, which is A equal 1, 2, 3, 2, 4, 5, 1, 1, 1. Okay. In order to get the row space, the basis for row space, okay, which are the unique vectors, the generators they are called, that are linearly independent, we need to do a row reduce. Okay, how to actually do that? So you need at first, okay, 1, 2, 3, 2, 4, 6, 1, 1, 1. Let's start removing or like triangularizing this matrix. Okay, so you have in the lower row, which is 1, 1, 1. Okay, let's make it 0. So we need to combine it to start doing combinations like R3 is equal to R3 minus R1. Okay, which means that 1 minus 1, 0, 1 minus 2 minus 1, then 1 minus 3 minus 2. Okay, so we've gotten rid of this first element and we've rendered it 0 in the third row. Okay, now at the same time, R2 is equal to R2 minus 2R1. Okay, so R2 here is equal to R2 minus 2R1. So, okay, row 2 minus 2 times row 1, 2 minus 2, which is minus 2 times 1 is equal to 0. 4 minus 2 times 2, 4 minus 4 also equal to 0. 6 minus 3 times 2, which is also 0. Okay? Okay, then after that, what else can we do? We need to do also, nullify this value. So, yeah. This row, yeah, 2 times this row plus the first row, I think. No, it won't work that way. Okay, you keep reducing it so that we end up with this triangular form. We've done the same thing, the same process before. Okay, now the row space is made of all the unique rows, okay, which are 1, 2, 3, that's the first one, and 0, 1, 2. Now 0, 0, 0 cannot be counted. Why? Because it makes it linearly dependent. Okay, so row rank is equal to, the rank is equal to, which is the number of unique vectors that are generators. Okay, 0, 0, 0, it's a 0 vector, so it cannot be counted. Why? Because it becomes a linear combination that when you add to something, you can get, 1, 2, 3 plus 0, 0, 0, it will end up with 1, 2, 3, which already is existing as a vector. Okay, so the rank is the set of vectors which are generators, unique generators, and linearly independent. Null space. How do we get the null space? We simply solve AX equal 0, with A being the set of rows that form the linear independent components of the space. Okay, so these are only the linear independent rows, namely 1, 2, 3 and 0, 1, 2 that we've gotten from row reducing the matrix. Okay, now 0, 0, 0 cannot be counted. Why? Because it renders this space independent. Okay, dependent, sorry. So it cannot be counted as a basis. It cannot be a generator. Why? Because its combination with 1, 2, 3 gives back 1, 2, 3, which already exists. Okay, so the unique linearly independent vectors are 1, 2, 3, 0, 1, 2. Okay, that they are completely linearly independent and from which you can generate other vectors. So the row rank is equal to, as a reminder of the previous slide of what we've previously explained. So you take these two rows, 1, 2, 3, 0, 1, 2, then 1, 2, 3, 0, 1, 2, you multiply them by x, which is the set of column variables, vector. So x1, x2, x3, or xyz, if you will. So 1, 2, 3, 0, 1, 2 multiplied by x1, x2, x3 is equal to 0. We're trying to solve this equation to get what we have as a span, in such case, the solution for this equation. Okay, so the first equation is x1 plus 2x2 plus 3x3 is equal to 0. Okay, so x1 plus 2x2 plus 3x3 is equal to 0. Second equation is 0 plus x2 plus 2x3 is equal to 0. Okay, so what we get is you have x2 is equal to minus 2x3. Okay, then you replace x2 by minus 2x3, so you get from the first equation x1 is equal to x3. So x is equal to x1, x2, x3. You replace each one of these variables by its value in respect of x3. So x1 is equal to x3. Okay, so equal x3 times 1. Then x2 is equal to minus 2x3, so minus 2 here, x3 on the outside, and finally x3, which is simply 1. Okay, So the null space is equal to the span of 1 minus 2, 1. Nullity is equal to 1, which is the number of vectors within that span. Check rank nullity. Okay, so the rank is equal to nullity equal to 1, and 2 plus 1, okay, which is rank plus nullity, gives us 3, which is equal to what? To n, or the dimension of the original matrix A, which was 3 by 3. So it has been proven. Rank nullity theorem for an m by n matrix A. Rank of A plus nullity of A should be equal to n, where rank of A, I think it should be n by n matrix, okay, where rank of A is equal to the dimension of the column space, meaning the number of pivot columns within RREF, okay, reduced row. Then nullity of A is equal to the dimension of the null space, so the number of free variables in AX equals 0 that we've seen one moment ago. N is the number of columns of A in such case, okay? So intuitive meaning, when solving AX is equal to 0, some of the variables are pivot variables determined by the equations. These correspond to rank. Actually, for AX equals 0, they correspond to nullity, okay, not rank, okay? Now, the free pivots themselves, before AX is equal to 0, the number of columns that are independent in RREF, they are the rank. So rank plus nullity should be equal to n. Together, total variables is equal to pivot variables plus free variables. So n is equal to rank plus nullity. Another exercise. Let V, the space, be equal to R3. So the dimension is 3. Are these subspaces? Let us check it. So for A, the first one, is it a subspace? Okay, W is equal to XYZ, for Z equal to X minus Y. Now, starting from A. For W to be a subspace, it has to satisfy the three following premises. Zero vector, closed under addition, and closed under scalar multiplication. Okay, so zero vector. Let U be equal to 0, 0, 0. Okay, Z is equal to 2x minus y. So Z minus 2x plus y is equal to 0. If we replace x, y, and z with 0, we get 0, correct? So 0 exists within this subspace. So let me go over it again. So for W, okay, let's us check this zero vector. How to check the zero vector if it is existing within the space W? You simply replace zxy by 0, 0, 0, by the zero vector, okay? First, to make it more neat, you move the right side of the equation to the left, so you end up with z minus 2x plus y. Okay, you replace zx and y by 0, which becomes 0 minus 2 times 0 plus 0 equals 0, which exists within W space. So the first condition has been met. Now, second condition, addition, which is U plus V. Okay, so let's say you have a U vector within W and a V vector also existing in W. U has the following coordinates, x1, y1, z1, and V has x2, y2, z2. Okay. Then we want to prove that U plus V is equal to x1 plus x2, y1 plus y2, z1 plus z2. Okay, so you simply replace z by z1 plus z2, x by x1 and plus x2, and y by y1 plus y2. Let us solve it, okay? So we've gotten this equation. We replace z by z1 plus z2, which is U plus V, x by x1 plus x2, and y by y1 plus y2. Okay, so you have that z1 plus z2 minus 2 times x1 plus x2 plus y1 plus y2 is equal to 0. You break it down. Okay, so you remove the ones with one index, okay, with index 1 to one side, and the arguments with index number 2 to the other side. So you get z1 minus 2x1 plus y1, that's the first, plus z2 minus 2x2 plus y2 is equal to 0. You replace z1 minus 2x1 plus y1 with what? With u1 or u, okay? And the second part by v, which is corresponding to the coordinates of v. So you get u plus v is equal to 0, okay? So you replace it, we get 0. Hence, it is closed under addition, okay? So you see, since u is equal to 0, u plus v is also equal to 0. Why? Because u is equal to 0 and v is equal to 0, closed under w, okay? So u alone, u for x1, y1, z1 is equal to 0, okay, when you replace it within this equation. And v, which has the argument x2, y2, z2, the following arguments, okay, x2, y2, z2, when you replace them within the equation, you get 0 as well. So u plus v, you replace x, y, z with x1 plus x2, y1 plus y2, z1 plus z2, you get from it also 0, okay? So you get u plus v is equal to 0, hence it is closed under addition. Now, let us check if it's closed under scalar multiplication. So c times u is equal to cx, cy, cz. Okay, so if we multiply z minus 2x plus y, each argument by c is equal to c times z, minus 2cx plus cy is equal to 0 for x, y, z is equal to 0. So it becomes 0. Hence, it's closed under scalar multiplication since it satisfies, since this w here satisfies the three conditions. This means it is definitely a subspace. Now, in the meantime, try to solve b, which is the second part, the second exercise. Okay, b, w is equal to x, y, z, for z equal to x minus y plus 1. Prove that it is a subspace. First, let us check if 0 vector is available within w or exists in w. Okay, so you have for u equals 0, 0, 0, let us replace z, x, and y with 0. So you get 0 minus 2 times 0 plus 0 minus 1, which is equal to 1, different than 0. Hence, it's not a subspace. Why? Because 0 vector does not exist. Okay, 0 vector is not available. More than that, if you go and check like the scalability, you check if it's additive, it will give you the same result. Why? Because you won't render it, like it won't achieve a 0 vector value. Hence, it's not a subspace because you still carry this one number that will render it always different than 0. Another exercise, let R3 be in R2, okay? So transformation here, x, y, z is equal to x plus y, y plus z. The transformation from the third dimension into the second dimension. At first, find kernel of t and a basis for it. Then find an image of t and its dimension. You can pause the video. Try to solve it yourself first before coming back. Okay, let's look at the vectors that will send the transformation to 0. You have x plus y, you place it equal to 0, and y plus z also equal to 0 to find for which values of x and y you get 0. Okay? Now, and z of course. So x plus y equal to 0, then x is equal to minus y. Y plus z is equal to 0, so y is equal to minus z. Hence, you get, okay, so x is equal to 1. Now we need to, parameterize a value. So let's say x is equal to 1, okay? Then since y is equal to, or since x is equal to minus y, so y is equal to minus x, which is minus 1. And y equal to minus z, so z is equal to minus y, which is also plus 1. Hence, the kernel of t is equal to the span of 1 minus 1, 1. Okay? So, and hence the basis for kernel of t is simply this vector, which is 1 minus 1, 1. Okay? It's the only generator. The dimension of this kernel, which is the number of the vectors that we found as generators, is 1. Now let's solve the second part, which is b. You can pause the video if you want to solve it first before getting back to the solution. Let's find an image of t and its dimension. Okay, so how do we actually do that? Okay, at first, this can be placed or represented in a matrix in the following way. So you have, that would be the first row. It has 1 for x, 1 for y, and 0 for z because z is not available for the first argument here, correct? So 1, 1, 0. As for the second row, it doesn't have an x, it has 1 multiplying y and 1 multiplying z, so it's 0, 1, 1. Okay? So these are the bases for t. Okay. Now, again, this is a, so x, we need to find a times x. X is equal to x, y, z being, the three variables. So we need to multiply them to find the solutions. Okay. Actually, the transformation itself is a times x is equal to t. This is the byproduct of this multiplication. This is the solution. But the columns, now we're more interested with the image, which is the columns, okay? So the columns are 1, 0, 1, 1, and 0, 1. Let's find which ones are the unique columns that form the basis for the columns, okay? So you have, or the ones that are linearly independent. These are simply 1, 0, and 0, 1. Okay, why is the column in the middle counted out? And this is a serious question, okay? Why is that? This is due to the fact that if we add the first column to the third column, you end up with the result being the second column. So 1, 0 plus 0, 1 is simply 1, 1, this column. So this one should be removed. Why? Because it's linearly dependent. Meanwhile, 1, 0 and 0, 1 are the generators. They are linearly independent, meaning that you cannot get one vector from the other. You cannot get this vector from this vector or vice versa. Meanwhile, the 1, 1 vector, the 1, 1 column, you can get it by combining the first column and the third column by adding them up. Okay, so together they form the middle columns. So the rank of A is 2, which is the number of independent vectors, namely 1, 0, and 0, 1. Image of T is equal to R2, which is the number of these vectors, okay, the rank. Basis for the image of T is 1, 0, 0, 1, that's the basis. Or we can choose 1, 0, 1, 1 also, okay. So two of these three vectors. The dimension of image of T is equal to, which is the number of linearly independent vectors. Rank nullity, let's check the rank nullity. It is equal to the dimension of the kernel of T plus the dimension of the image of T. Okay, dimension of kernel of T, which is 1. We've seen it in the previous solution. Let's get back to it. Okay, so this was the dimension for the kernel, one vector you have. Okay, plus the dimension of the image of T, which is 2. So 1 plus 2 is equal to 3, which gives us back the dimension for the space, the original space, okay, which is 3. Another exercise, let W be equal to xyz within R3. X minus y plus 2z is equal to 0. That's the first equation. And 2x plus y minus z is equal to 0. Show that W is a subspace of R3. First question. And find a basis for W and compute dimension of W. That's the second question. You can pause the video. Try to take a jab at this exercise. Try to solve it yourself first before coming back to the solution. All right, now let's check if x minus y plus 2z is equal to 0 is a subspace. Okay, so first we need to verify if 0 vector exists within W. So let u be equal to 0, 0, 0. You replace x, y, and z within this equation by 0, 0, and 0. Okay, so it becomes 0 minus 0, which is the y, plus 2 times 0 is equal to 0 vector. It exists within W. So this is the first condition. It has been satisfied, the first criteria. Second criteria, checking if it is closed under additivity. So u, let's say u is equal to x1, y1, z1, v equal x2, y2, z2. U plus v is x1 plus x2, y1 plus y2, z1 plus z2. Okay, so x1 plus x2, you replace x with x1 plus x2 minus y1 plus y2 instead of y plus 2 times z1 plus z2 equal to x1 minus y1 plus 2z1 plus x2 minus y2 plus 2z2 is equal to 0. Okay, so why? Because the first one is equal to 0, which is the first u. Okay, u is 0, 0, 0, and v also 0, 0, 0. So the sum of them is equal to 0. Okay, so which gives you x1 and 2, 0, y1, 2, 0, z1 and 2 are 0. So this entire sum is equal to 0. Hence, it is additive and it is enclosed, like it is closed under additivity within W. Okay, so this is the second condition that has been met. Now, finally, checking if it is closed under scalar multiplication. So if you multiply u with c, you get c times x minus cy plus 2cz, which is also equal to 0 for xyz equal to 0. Therefore, the first equation is a subspace. So we verified that this first equation is indeed a subspace based on these conditions being met. Now let us check if the second equation is also a subspace. Okay, so you have 2x plus y minus z is equal to 0. Is it a subspace? Okay, what are the three conditions needed? First, the no vector, the 0 vector should exist. Then it should be additive under closed under with additivity under W, and also closed under scalar multiplication. So let's check the three premises. 2x plus y minus z is equal to 0. Okay, 0 vector doesn't exist. Let u be equal to 0, 0, 0. You replace x, y, z by 0, and you still end up getting 0 vector, which exists within W. Okay, so it's still under the subspace W. Second, checking if it is closed under additivity. So u equal x1, y1, z1, v equal x2, y2, z2. U plus v is equal to x1 plus x2, y1 plus y2, z1 plus z2. Okay, let's replace x, y, and z with x1 plus x2, y1 plus y2, etc. Okay, respect. So within the equation, of course. So 2 times x1 plus x2 plus y, which is y1 plus y2, minus z, which is minus z1 plus z2. You end up with 2x1 plus y1 minus z1 plus 2x2 plus y2 minus z2, which is equal to 0, given that x1, y1, z1 is 0 and x2, y2, z2 is 0. So it is closed under additivity. Now, finally, we need to check if it's closed under scalar multiplication. So you multiply by c. Okay, cu is equal to cx, cy, cz. Okay, yeah, which is c times 2x plus cy minus cz is equal to 0, since x and y, or for x, y, and z equal to 0. Hence, also, okay, it is closed under scalar multiplication, and the second equation is also a subspace. Now, let's find a basis for w and compute the dimension of w. Okay. First, we need to place both of these two equations. Okay, let's take x equal 1 as a parameter, since we have 3 variables and 2 equations. So x is supposedly 1. Okay, we end up with 1 minus y plus 2z equals 0, first equation. 2 plus y minus z is equal to 0. If we add 1 and 2, these two equations, okay, you get 3 minus y plus y cancel out, and 2z minus z becomes plus z. So 3 plus z is equal to 0. So z is equal to minus 3. Now, okay, you replace this value of z within one of the equations, let's say the first one. So 1 minus y plus 2 times z, which is minus 3, is equal to 0. Okay, 2 times minus 3 is minus 6. So minus y minus 6 plus 1, which is minus 5. Hence, y is equal to minus 5. So xyz is equal to 1, which is the value that we supposed at first. Okay, we suggested. Then for x is equal to 1, y equal minus 5, and z is equal to minus 3. So the span is, for w, 1 minus 5 minus 3. And this is also the basis. Okay, the basis is this unique vector, 1 minus 5 minus 3. Okay, and yeah, it's not like the span is equal. W is equal to the span of 1 minus 5 minus 3. This is what I meant. And the dimension is the number of these vectors, these basis vectors that we've gotten that are unique. The dimension of W is equal to 1. It is equal to 1 since we only have one vector. Another exercise, okay, let T be the transformation from the 3 dimensions, the dimension 3 to the second dimension. Okay, let it be T x y z is equal to x plus y and y plus z. Find the kernel T, the image of T, and their dimensions, and give the basis. Okay, at first, to find the kernel, we need to solve x plus y equals 0 and y plus z is equal to 0. Okay, so you get x is equal to minus y, y equal minus z. Okay, let's fix all of them over y. So this is y. Okay, fixed. X is equal to minus y. So instead of x, you place y, minus y, sorry. And for z, okay, so y equal minus z, so z is equal to minus y. So you get minus y, and minus y. You take y equal to 1, for example, so the kernel of t is equal to the span of minus 1. 1 minus 1. The dimension of this kernel is this only vector, is the number of unique vectors that we've gotten, which is one vector here in such case. Okay, so the dimension of ker t is equal to 1. For the image, any AB within R square, okay, which are here in such case the columns, not the rows, can be obtained. Okay, choose y freely. So you have x is equal to a minus y, z is equal to b minus y. Okay, the image of t becomes 1, 0, and 0, 1. Okay, so if we place x, y, and y, z underneath each other, basically, okay, so x is equal to minus y, correct? You add to them a, an argument, and z, you add to it an argument, which is b minus y. Yeah, doesn't matter. So the basis is you have 0, 1, okay, or sorry, 1, 0, that's the first column, and 0, 1. The dimension of the image is equal to, okay, so let's suppose you have x plus y, okay, plus z is equal to 0, so 1, 1, 0, correct? That's the first row. Then y plus z is equal to 0, so you have x is 0 here, y is 1, and z is equal to 1. Okay? These are the bases, with 1, 1 being what? The combination of the two columns. That's why 1, 1 cannot be counted in. So the bases, forget about these two lines. They might be confusing. The image of t is the columns. So you place these two rows on top of each other. The first row is x, y, and z is 0, so 1, 1, 0. Second row is y plus z, okay, with x equals 0 because there's no x here. Y is multiplied by 1 and z by 1. So the two unique columns which form the basis are 1, 0, 0, 1, or 1, 1 and 1, 0, okay, or 1, 1 and 0, 1. It doesn't matter. But the most important thing that is that they need to be 2 exactly, okay, which is equal to the number of rows. And you notice here that 1, 1 is not useful since it is the combination of the first and third column. So the dimension of the image of t is equal to 2, which is the number of linearly independent vectors that are the linearly independent columns. In this case, 1, 0, and 0, 1. Again, you can choose 1, 0, and 1, 1. It's okay. Let's check the rank nullity. The rank is equal to 1, which is, the number, the dimension of curve t, plus, actually the rank is, you have the dimension curve t, that's the nullity, which is 1, plus the rank, which is the number of the basis vectors that are unique, 2, is equal to 3, which is equal to what? The dimension of R3 that we've started with. Okay? Before the transformation, before it was transformed into R2, a two-dimensional space. Another exercise. Let U be equal to the span of 1, 0, 1, 0, 1, 1, and V equals span 1, 1, 0. Find the dimension of U plus V, and U intersect V. You can pause the video, try to think about it at first before getting to our solution. All right. So the generators are the following. You have 1, 0, 1, 0, 1, 1, and 1, 1, 0. They are completely independent. You cannot get one of them from the other. So the three are independent. They form the full span of U plus V. So the rank is 3, which is the number of basis the basis vectors, okay? The generators. Number of generators or linearly independent vectors is 3. So the rank is 3. Hence the dimension of U plus V is equal to 3, which is dimension R3. Okay, by formula. Now, dimension of U intersection with V is equal to dim U, dimension of U plus dimension of V, minus the dimension of U plus V, based on the formula, which is equal to dimension of U is 2, plus dimension of V is 1 minus dimension of u plus v, which is 3. So 3 minus 3 is equal to 0. There are no intersections. There's no area of intersection between u and v. They are completely independent for the spaces, okay? Which also, by the way, conforms with the fact that the vectors within these two spaces also are independent. Given v1 equal 1, 2, 3, v2, 2, 4, 6, v3, 0, 1, 1, and r3. 3 vectors. Okay. Are they linearly independent? And find a basis for their span and dimension, and its dimension. Again, you can pause first and then come back later to the solution if you want to try to solve. Okay, so at first we have, if you notice, v2 is equal to 2 multiplied by v1. Because if you multiply v1 by 2, you get 2 times 1, and 2 times 2, 4, and 6, which is 2, 4, 6. This is v2. Okay, so v2 is an actual combination of v1, is a scalar multiplication of v1. So these vectors are linearly dependent. Okay, let's check v1 and v3. So between v1 and v2, they are dependent. For v1 and v3, okay, only trivial combinations give 0, so they are independent. Okay, they are completely unique. Hence, v1 and v3 is the basis. Okay, these are the two generators, the two unique and uniquely independent vectors that cannot come as a combination from each other. Like you cannot generate one from the other, one vector from the other, so they form the basis. Okay, hence the rank is also 2. So the dimension of the span of v1, v2, v3 is equal to, okay? Why? Because you have v1 and v3 only. v2 does not count. Now, let p2 be polynomial of a degree less than or equal to. Okay, that's another exercise, I think. Okay, we might have not completely finished the first part. Yeah, the basis for the span. Oh, yeah, we've already found the basis. Okay, great. Now, let P2 be polynomials of degree less than or equal to. Define W equal P within P2 and P of 1 equal to 0. Show W is a subspace and find a basis. Okay. If P1 equal Q1 equals 0, then P plus Q of 1 is equal to 0. And alpha P of 1 is equal to 0, so W is a subspace. So it conforms or satisfies the three conditions of nullability, of additional closed under addition, and closed under a scalar multiplication. Okay? So if P of 1 is equal to 0, Q of 1 would be equal to 0, P plus Q of 1 is equal to 0, and alpha P of 1 is equal to 0. Since P of 1 is already 0, whatever you multiply by it would also give a 0 vector, so it is closed under scalar multiplication. Okay? Hence, W is proven to be a subspace. Now, general PT, okay, let's assume P of t is a quadratic equation because it's a polynomial. Is equal to at squared plus bt plus c. P1 is a plus b plus c is equal to 0. C is equal to minus a plus b. Then P of t is equal to a times t squared minus 1, okay, plus b t minus 1. All right, so yeah, because we're supposing that c is equal to 1, I think. Okay, I'm not getting, yeah, c is equal to minus a plus b. So we replace c with minus a plus b, I believe, okay? And we've gotten this equation. So we replace c by minus a plus b, and you get p of t is equal to a times t squared minus 1 plus b times t minus 1. Okay? So, okay, the first basis is, or the first, like, the first basis is t squared minus 1. Second is t minus 1 with dimension of w of the subspace is equal to, we have two unique vectors. Okay? So you notice here we have A being like, yeah, so you have A, B, and C. C is equal to minus A plus B. Okay, P of T is equal to AT squared minus 1 plus BT minus 1. Okay, A and B acting like variables here. So the first vector, the first basis is t squared minus 1. Second is t minus 1 with dimension of w equal 2. Because we have only two unique vectors within the basis.